matrices. And we are moving to our last topic. And it is in chapter 8, section 8.2. It is to use Laplace transform and its inverse to solve differential equations. Before we really get to the point to solve differential equations with Laplace transform, we still have a little bit more work to prepare. And so here it is the work I'm talking about. First of all, recall the definition of the Laplace transform. It is integral transform. It is defined in this fashion. And then when we can f, it is a function, and then it has derivative, right? So let's pretend try to calculate the transform of the derivative. So indeed, according to the definition, derivative is a function. So it is always the exponential term times the function. This time the derivative is a function. And also I'm thinking to using integration by parts. So you take a look if this writing makes sense to you. F prime of t dt simply can be written as df of t. Differential of the function, it is derivative times dt. So they are the same. Okay, they are the same. And then using this fashion, I'm using the integration by parts, u dv. Integration by parts, u dv. It will turn to be u times v minus antiderivative v du. Integration by parts. I think I have the integration by parts formula in the previous section, so maybe helpful. Let's try to copy down the integration by parts formula. It's right here. This is the formula I'm talking about, the integration by parts. Try to see if I can copy and paste to the new place quickly. We're in section 8.2. We are considering the transformation of derivatives using integration by parts. Yep. Actually, I copied it 2 times. I only need 1, right? Integration by parts. This is integration by parts I'm talking about. U times v minus the antiderivative. Actually, I just realized it should be antiderivative v du. V right here. V right here. And before I forget, I suppose I want to make an update for the other part too. Integration by parts. Yeah, it should be antiderivative of v du. I think both places are corrected. And then move back to our current topic, transform of derivatives. Transform of derivatives. This is where we are. Transform of the derivative. Okay, in the fashion of u dv. Using integration by parts, it's u times v minus the antiderivative v du. And then also take a quick look about the first term, u times v. Certainly this is improper integral, so u times v is still the improper integral using the fundamental theorem calculus. Okay, and this time let's assume indeed the exponential term, because t is approaching to infinity. Also let's say s is positive. Okay, so indeed the exponential term, it is at the bottom. And indeed, you may want to understand that the exponential function, usually it is considered as the function grows at the fastest rate, which means the other functions is not comparable to the exponential function. So really, it's fair to say when we consider such a limit, okay, as t approaches to infinity, f of t over e to the st, because the exponential term grows a lot faster, and you can use the L'Hopital rule, we can say this limit is 0. Limit is 0 as t approaches to infinity. And when t is 0, this entire term, the exponential term, it is 1, so it is just f of 0. This term, it is f of 0. And also look at this term part, antiderivative v du. Indeed, this differential part, using the chain rule, we got another minus s. Another minus s. Okay, negative minus negative s, that's a plus. And then this turns out to be the transform of the original function. So this is the conclusion I'm trying to make. The transform of the derivative is s times the transform of the original function minus the function at 0. The function at 0. And indeed, this is not the only conclusion we have. We could make similar conclusions. Certainly, you are going to calculate the transform of those other derivatives, higher order derivatives using the definition. And eventually, you will see the transform of the second order derivative and the transform of the third order derivative. And we could you have the transform of the fourth order derivative. But anyway, save time, I guess. Indeed, for our class, we will only look at the transform of the second order derivative. So these two formulas are good enough. Transform of the derivative and the second order derivative, they both turn out to be the transform of the original function. Okay. And now let's take a quick look. How do we use the Laplace transform to solve differential equations? This is the example 1 on the textbook, example 1. And this is the differential equation. And we are having two initial values. Together, it is the differential equation with the initial values together. That is an initial value problem. And then we're supposed to have a unique solution. Okay. This time we want to solve this differential equation using the Laplace transform. So what I did first here is I applied the Laplace transform to the entire equation, the left and the right. And the right, I suppose it's easier to understand, the transform of 0. Because it is the integral transform, the integral of 0, it is still 0. The transform 0, it is still 0. Okay. And to the left, the transform of the second order derivative of this entire left-hand side. Because the Laplace transform, it is linear, which really allows us to look at the transform of each term, 3 terms separately. Also, we can take out the constants there, because the Laplace transform is linear. Okay. And then remember the transform of the second order derivative and the first order derivative, as we just calculated, this is transform of the first order derivative, transform of the second order derivative. So I replace the transform of the second order derivative with the result right here. And I did the same for the transform of the second order derivative. Read those formulas carefully, okay? And then still a lot of things indeed. Okay, you want to be very careful what we really want to achieve. Okay, I'm saying s squared, that should be fine, right? And really what we are looking for here, it is the transform of y. Transform of y. Y of 0. And y prime 0, these are given numbers. S, it is a variable, and also we know y of 0. Okay, so we are having 3 terms involving with transform of y. These are the like terms. So s squared minus 2s minus 3. And the transform of y can be considered a function, the common term, the like term. So I take out the coefficients for the transform of y, and then what we are having here is s times y of 0 is 2. That is the initial value part. So s times 2 minus y prime 0, that's minus negative 10. And also I believe we have another thing here, right? 2 times negative y of 0. Negative 2 times negative y of 0, which really tends to be 2 negatives. Y of 0, it is y of 0, it is 2, and I think probably it would make more sense if I just put this as a plus sign here, or minus, or maybe let me still keep a minus sign there, because eventually I'm going to move this number, well, minus negative 10, that's plus 10, minus 2 times negative 2, that's plus 4, minus 4, plus 14. Because eventually I'm moving these terms to the right. So what I figured out here is the transform of y will have to be this rational function in terms of s, right? So would it make sense to you to this moment to solve the differential equation? It is to find out the inverse Laplace transform. And this part of the inverse Laplace transform was covered in the previous section, and then we can use partial fractions. Numerator can be factored. Okay, I mean denominator can be factored. So with partial fractions, we realize this fraction really it is the same as those two separated fractions. And then indeed, we do have the inverse transform of each part, each term. So indeed, what we figured out here is y it is negative 2 times e to the 3t plus 4 times e to the negative t. We just solved an initial value problem using the Laplace transform. To solve a differential equation, we do need to use a Laplace transform, the inverse transform, and the transform of derivatives. Hey, thank you for watching, and I'll see you next time.